So we will study electron absorption spectra of transition metal complexes. Now, what is it? It is the study of excitation of a chemical species from its ground state electronic energy level to an excited state electronic energy level by absorption of electromagnetic radiations. जब भी आपका कोई आयन कोई केमिकल स्पीसीज जैसे इलेक्ट्रॉन जो है वो इलेक्ट्रोमैग्नेटिक रेडिएशन को एब्जॉर्ब करता है, देन व्हाट हैपन्स, the excitation of the electron, it takes place from its ground energy level to its excited state energy level. So जो इलेक्ट्रॉन एब्जॉर्प्शन है, इलेक्ट्रॉन एब्जॉर्प्शन स्पेक्ट्रा है ट्रांजिशन मेटल कॉम्प्लेक्सेस का, it tells us about this feature of transition metal complexes. So अब ये जो स्टडी है, it gives us ये बहुत important information about colors of complexes, why the complexes are colored, what is the reason behind the colored complexes, and what is why the magnitude of energy gaps between ground electronic energy state and excited electronic energy state. Now why different magnitudes, अलग अलग magnitude क्यों है energy gap के ground electronic energy state में और excited electronic energy state में? Like for tetrahedral complex में different होगा, octahedral में अलग होगा, square planar geometry में it will be different, the difference between energy levels. So ये जो explanation है that is given by electron absorption spectra of transition metal complexes. Now what is the extent? It also tells about what is the extent of covalent character in metal ligand bonds, what is the geometry of complex, position of metal ions, the ligands in spectrochemical and nephelauxetic series. Now crystal field spectra arises, due to excitation of electron of a metal ion from ground. This arises due to splitting of d level, and why does the splitting takes place? Because of the differential approach of the ligands, क्योंकि जो ligands है उनकी approach जो है central metal ion की तरफ different होती है, तो that leads to splitting, that we have studied in the previous part. So next we have atomic spectroscopy. So for this we have to study the atomic spectroscopy. Atomic spectroscopy, what is it? Now there are जो आपका electron है it exhibits two types of angular momenta. One is orbital angular momentum and another is spin angular momentum. Two types of angular momenta, they are exhibited by electron. One is orbital and another is spin angular momentum. So according to pre-wave mechanical concept, an electronic this is very important line, an electron generates orbital angular momentum. Orbital angular momentum is denoted by L. It arises by virtue of movement of electron around in an orbit. Due to its movement in an orbit, it is moving around the nucleus. So which is a vector quantity and is perpendicular to the plane of orbit containing the electron. You can see here it is moving around, and the this angular momentum that is perpendicular to the plane of orbit containing the electron. That is clear from here. So we can say that L is equal to magnitude of L, that is angular momentum, that is equal to L x square, y square and z square. We have three directions, Lx, Ly and Lz. I have told you, and you know about these directions, x, y and z directions. So where Lx, Ly and Lz are components of L along x, y and z axis, the magnitude of vector L, that is equal to under root L into L plus 1 h upon 2 pi, where the angular momentum where L is the angular momentum quantum number. L is the azimuthal quantum number. ये वही उसी के बारे में बात कर रहे हैं. What is that? L is the angular azimuthal quantum number, and also we can say angular momentum quantum number. Now next we have one thing very important which you have to notice, that L, this L and L, they represent different quantities. These these L, this L is, this capital L is azimuthal quantum number or angular momentum quantum number, whereas this L, which is in brackets, this is the vector quantity, the vector L, that is allowed to L plus 1 orientations or positions in space about any given direction. Generally we take the Z direction. About a particular direction, how many orientations L can have? 12 plus 1 orientations it can have, in such a manner that its component along this direction, that is ML, can have values. It can have values ranging from L, H, L plus L, H upon 2 pi to minus L, H upon 2 pi, depending upon orientation of the vector L. Now this L is the vector quantity which represents orientations or positions in space in a given direction. और direction हम कौन सी लेते हैं? We take the Z direction into consideration. This L represent how many orientations are possible. Now we will take here examples. Orientations of when L is equal to 2 along Z axis. You know the values are from -2 to +2. M की values कितनी होती हैं? For L is equal to 2. You know that -2 to +2. So these are the orientations which represent. This is 0, ML equals to 0. The जो values इसके below हैं, they are in minus, and the one which are above it are in plus. And so this is for L equals to 2. Now next we have, now if we apply external magnetic field along the same, direction, that is Z direction, please pay attention here. These orientations were there when external field was not applied. Now if we apply an external magnetic field along the same direction, that is Z direction, it is the component L along the direction, along this direction with, for example, ML, which interacts with external magnetic field. If there are two L plus 1 values of ML, then obviously there would be 2L plus 1 interactions of ML with external magnetic field, and each interaction of this type would have the different energy. And in the absence of external magnetic field, all the orientations would be of equal energy, and L may have any 2L plus 1 orientations in space. Now if we apply external magnetic field, then what will happen? So we have 2L plus 1 values of ML. You know there were 5 from -2 to +2, 2L plus 1. when L is equal to 2, 5 values इसकी possible हैं, जो हमने पीछे example लिया था, from -2 to 2, -2, -1, 0, 1, 2. And then if we apply external magnetic field, then these interactions of ML, each of these orientation, that will interact with external magnetic field, and each interaction of this type would be of different energy. And when there is absence of external magnetic field, all the orientations would be of equal energy, and L may have 2L plus 1 orientations in space. Now another thing is that the electron is also spinning around its own axis. Yes, in addition to orbital angular momentum arises by virtue of the fact that electron that is rotating around the in an orbit around the nucleus, but electron is also spinning around its own axis. The spinning motion generates spin angular momentum S, which again is a vector quantity and is directed along the spinning axis of electron. So if you will, please pay attention to the last figure, the figure in the last, and there in the, if we in the last page there is a figure where there is spin angular momentum. I'll show you this. See, this is the spin angular momentum representation of spin angular, because it is moving around its own axis. So this momentum arises by virtue of movement of electron around its own axis. So as a result of this, another thing is that electron is also spinning around its own axis. The spinning motion generates spin angular momentum S, which is again a vector quantity and is directed along the spinning axis of the electron. I have shown you that just now. The magnitude of vector S, that is equal to under root S into S plus 1 h upon 2 pi, where S is the spin quantum number. Then next we have, now we will discuss the spin angular momentum. Now the position of this vector S in space is quantized in the sense that it is allowed a fixed number of orientations in space about any direction. Let us take regard it as the Z direction. We always take by default the Z direction. So each orientation of vector S, this is the vector representation, and the S was representing the spin quantum number. Each orientation of vector S in space has component Sz or Ms along Z direction. It represents the component of vector S, Ms or Sz. The two Ms values for two orientations of S are plus 1 by 2 h upon 2 pi and minus 1 by 2 h upon 2 pi. These are the two values, plus and minus. Generally the value of the S that depends upon the that depends upon the clockwise, or we take or anti-clockwise rotation of the electron around its own axis. So the factor h upon 2 pi is omitted. We can write it in, दो वी जब हम स्पिन एंगुलर मोमेंटम को कंसिडर करते हैं तब हम h अपॉन 2 पाई इज कंसिडर्ड, बट फॉर ब्रेविटी और फॉर ब्रीफनेस इसको हम ओमिट भी कर सकते हैं. वी कैन जस्ट राइट दैट मैग्नीट्यूड ऑफ एंगुलर मोमेंटम can be written as under root 2 into 2 plus 1 h upon 2 pi. It is a common, it is a value which is we are writing here the magnitude, right? So we can write it without h upon 2 pi also. And for spin angular momentum 1 by 2, we can write it as 1 by 2 into 1 by 2 plus 1 without omitting h upon 2 pi. Then next we have coupling of single electron momenta. As L and S, each electron in a given electronic configuration, they are both L and S, they are vector quantities. Hence, like all other vector quantities, they can be combined to give a resultant vector. When two combining vectors precess about the direction of the resultant, such vectors are said to be coupled. Now, both L and S are orbital angular momentum vector quantity, and S, the vector of S, spin angular momentum, both are vector quantities, and they if we combine both of them, they give a resultant vector. We get a value of resultant vector. Now, when two combining vectors precess about the direction of the resultant, the vectors, they are said to be coupled. So these two vectors, they precess in the direction of the resultant. तो इनको हम coupled, so these vector quantities, they are called as coupled vector quantities. And the following types of coupling of single electron angular momentum vectors L and S are seen in free atoms or ions of elements. So what do we see? First type is SS coupling or spin-spin coupling. First type of coupling which is seen. The spin angular momentum vector S1 and S2, they couple to give a resultant spin angular momentum vector S, the single electron vectors S1 and S2 can couple only in certain fixed inclinations of S1 and S2. Each fixed inclination of S1 with S2 will give its own resultant S. So S1 and S2 are the two vectors for spin angular momentum S. So these two vectors S1 and S2, they couple with each other in a certain fixed inclination, and they give their resultant vector S. Now the magnitude of resultant spin angular momentum S, that is equal to under root S into S plus 1, where S is resultant spin angular momentum. This will be more clear by this figure. Now the position of, we can see here, the position of vector in space, that is also quantized in the sense that it is allowed a fixed number of orientation. Yes, it has a fixed number of orientations in space about any direction, and direction which we take, जो हम लेते हैं, that is z direction. Each orientation of vector S in space has component S2 or ms along z direction. The two ms values for two orientations of S are plus 1 by 2 h upon 2 pi and minus 1 by 2 h upon 2 pi. These two values you can see, plus 1 by 2 and minus 1 by 2 h upon 2 pi. That is not written here, we're just writing the magnitude. These are allowed orientations for vector S equals to 1 by 2. Again, this is the same, that factor h upon 2 pi is it can be omitted for having the brevity. Now next we have this, we have SS coupling or spin coupling. This is what we are doing. So next we have, now S can have values ranging from S1 plus S2 and S1 minus S2. This implies that the resultant spin angular momentum, will also have two values. For example, if we consider two electron system or ion in a free state, the resultant spin angular momentum S will have two values, plus this either S, as we did, S1 plus S2, 1 by 2 plus 1 by 2, that is 1, or 1 by 2 minus 1 by 2, that is 0. Therefore the magnitude of vector S will also have two values, under root S into S plus 1 and with the जिसकी values, whose values are put here, S की value put कर दीजिए यहाँ, 1 by 2 that is equal to 1. So एक ये value होगी जहाँ पे 1 है S की value, तो उसको put कर दीजिए 1 into 1 plus 1, and another is 0, where 1 by 2 minus 1 by 2 is 0, 0 into 0 plus 1. Commonly the values will be 1 and 0. So the spin angular momentum vector will have 2 into 1 plus 3 orientations about z direction, whose z components along this axis, they will be minus 1, 0 and plus 1. We can see here for S equals to 1. Now if for the spin angular momentum vector 0, we have two vectors, one is 0 and one is 1. यहाँ से आया ये 1 and 0. For 1 there will be 3 values, and for the value 0 there will be only one value, that ms with 0. This will be the value. Two vectors we have, I'll again repeat, 1 and 0. और ये कहाँ से आया? Because there are two possible orientations, S1 plus S2 and S1 minus S2. So S1 plus अगर S2 है तो 1 है, S1 minus S2 है तो 0 है. तो अगर put these values इसमें, this is S की value अगर 1 है तो 1 into 1 plus 1 and 0 into 0 plus 1. तो 1 और 0 आपकी जो वैल्यू है that will be there. So the spin angular momentum vector 1 will have 2 into 1 plus 3 orientations in space about the z direction whose components along these directions, that is ms values, will be -1, 0 and +1. So, and while the spin angular momentum vector 0 has only one value of ms, that is 0. So, thank you.